Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about Newton's Cannonball. Newton's Cannonball, illustrated here. This is an illustration taken from the 1687 edition of Newton's masterwork, the Principia. And this drawing here, this cartoon, is incredibly moving. I find it incredibly moving because it summarizes in one image so many incredible ideas that have shaped and continue to shape our understanding of the world. So, what is going on in this picture? Let's dig in. So the cartoon illustrates this thought experiment, which Newton used to hypothesize that the force of gravity was a universal force. It not didn't just apply to the motion of objects on Earth. It also applied to the motion of celestial bodies in the heavens. And that was a fairly radical idea in 1687. But what is most powerful about Newton's thinking about gravity being a universal force was that he backed it up with rigorous mathematical demonstrations, which we will get to before too long. So, what is going on in this picture? So, Newton is imagining a tall mountain on Earth in which he has a very powerful cannon. And he's trying to plot what the trajectories would be if he launched the cannonball with an initial velocity, say, directed to the right. What would be the motion of said cannonball, neglecting for now the effect of drag? And you know already that if the force of gravity is a constant force pointing downward, then the trajectories that you get are parabolas. But what Newton was coming to realize that gravitation was a universal force, and there was a mathematical form for the force law, which we'll now write down. So Newton's law of gravity can be written mathematically in this form, and it says that if there are two masses, and for now we'll consider just point masses, m1 and m2 are the masses, and if we construct a vector r that goes from 1 to 2, a sort of position vector r, then there will be an attractive force that mass number one will exert on mass number two. And attractive is indicated by the fact that we have a minus sign here and the force points in the direction opposite to R. And the magnitude of that force will be some universal constant, which we'll call big G, times the product of the masses divided by the separation, the magnitude of the separation between the masses squared. We refer to this law of gravity as an inverse square law because the magnitude of the force depends on the 1 over the distance between the masses squared. So the first question that really we should at least mention, we'll get back to it in depth in a while, in a couple of days or so, but this law refers to point masses. And now we want to apply that law to the situation where, well, treating a cannonball as a point mass may not be such a bad approximation, but what about the Earth? The Earth is a really big ball here and the mass is spread out all over the place. What do we do about this force law, which applies to point masses? And one of Newton's crowning achievements was to show, he basically had to invent calculus to show this, that if you have a spherical mass like the Earth, uh, and you're going to apply the law of gravity, it will behave, as long as you're outside the Earth's surface, it will behave as if there were a point mass located right at the center of the Earth. So it's pretty easy to apply Newton's law of gravity to the situation. We're just going to treat the Earth as if all its mass were located right at the center of the Earth. So, with this insight, when you try to understand what happens when Newton's cannonball launches things with ever increasing velocities, they're obviously going to travel further. The situation is going to be different from the way we've been treating gravity previously. Previously, we had said that the gravitational force was a constant. Previously we just said that the gravitational force was equal to mg pointing vertically downward. But now you can see in this situation that the gravitational force is not going to remain constant throughout the motion, really for two reasons. One is the distance to the center of the Earth, r, is going to change. As you get closer to the Earth, the magnitude of this force is going to change. But not only that, the direction of the force is going to change. The direction of the force is always going to point towards the center of the Earth. So as you go further and further, um, the direction of the force is going to become more and more different from what it was originally. And so the trajectories that you get here are certainly not going to be parabolas. They turn out, as Newton was able to show, they turn out to be ellipses. And if the ellipse collides with the surface of the Earth, the trip is done. But if you give something a strong enough, big enough velocity, you can end up getting a closed orbit. And so that was one of Newton's great insights, was just with this law of gravity, a simple to write down law that he hypothesized was universally applicable. He could begin to describe not only what happens to things moving on Earth, but to the planets moving in the heavens. So when I see this figure, uh, all these centuries later, I am incredibly moved by it, just because the ideas embedded in it are so deep and have had such a profound influence on our view of the universe. And you will have a chance to simulate a Newton's Cannonball with a VPython simulation coming up on a assignment. So that is something that's pretty cool, something to look forward to. And let me conclude by pointing out sometimes the real world lives up to the cartoon version. This is Isaac Newton in 1687. This is Elon Musk in the year 2021 talking about realistically putting humans on board Newton's Cannonball and sending them on very quick trips from, say, New York to Shanghai in about 35 minutes or so, if you're willing to ride on one of Elon's rockets. So there's a great video which is linked. There's an assignment coming up on assignment 6, which has you explore this and this idea. And there's a wonderful promotional video, which SpaceX is very slick, is good at producing these very slick videos. And whether this will ever come to pass or not is anyone's guess, but it's pretty audacious even to be thinking about sending rockets with 200 people in them from New York to Shanghai in 38 minutes or whatever the travel time is. So pretty cool. And that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye bye.